Great. So welcome everyone. We're gonna hear about distributionally risk-receptive stochastic integer programming from Dr. Manish Bansal. He's an associate professor at Virginia Tech. And before that, he got his PhD at the Texas A&M University. And after that, he had a fellowship, a postdoctoral fellowship at the Northwestern University. His research focuses on the theory of mixed integer programming, stochastic programming, game theory, and a lot of other many interesting fields. He received multiple grants from the NSF, DoD, etc. And we're very happy to have him with us today.
Great. Thank you, organizing committee, for inviting me. This is a wonderful seminar series. I'm glad to be part of it. So like Sylvia mentioned, I'll be talking about distributionally risk-receptive and robust stochastic integer programs with application in the interdiction models. To start with, I'll start with the brief description of a network interdiction problem. Some of you might be already familiar with it. If you are, it will be a short tutorial for you. If you are not, again, it will be a short tutorial for you as well. So here is a shortest path problem. So let's say we are given a network, and I have to find the path from a shortest path from source to the destination T. In this graph, the numbers that are outside the parenthesis is the travel cost. And if you will solve any linear program, it will provide you a solution. S22 to T is the shortest path. But let's say we have to do this in an adversarial environment where there is a game that is being played between an adversary and a defender. And the adversary would like to destroy some of the arcs in this network with the objective of maximizing the minimum travel cost. So in this example, the numbers that are inside the parenthesis is the penalty cost, which means that the adversary, let's say up here, if adversary decided to attack arc S2, then the travel cost has become 2 plus 8, which is 10. Same if they decide to attack arc 1T, then the travel cost will increase from 4 to 8. So it's a two-player game where adversary would like, or it could be adversary, or it could be an interdictor, would like to decide which of these arcs, given the limited budget, they would like to attack so that they can maximize the minimum travel cost. So a deterministic network interdiction problem defined over a graph G with a set of nodes N and a set of arcs A can be very easily formulated, where you have two sets of decisions. Let's say XA are the decision variables corresponding to interdictor or attacker, which is 1 if interdictor decide to attack arc A and 0 otherwise. And YA is 1 if follower or defender or network user, I'm going to use these terms essentially for the follower. So follower decision is YA is 1 if follower travels along arc A. Some of the input data parameters that are given, which is CA is the cost associated with arc A, B is the interdiction budget, and DA is the penalty cost of interdicting arc A. So pretty much the way it will work is that attacker would like to maximize the minimum travel cost, but they have a fixed budget of B. So you have these cardinality constraints here, so which is summation of XA equal to B. And essentially for QX is the decision that will be made by a defender on the interdicted network. So once the attack has been done, so you have X, which is representing the attack. And this is just a shortest path problem, a linear program with flow balance constraints. And if XA is 1, then the cost to travel through arc A is CA plus DA. If XA is 0, then it is just CA. So it leads to this max-min problem that you would like to solve. An extension of this problem has also been studied called as the stochastic or risk-neutral network interdiction problem, denoted by SNIP, starting from Israeli in 1998 and Himiki and others in 2003. The assumptions were that the success of interdiction and the impact of the interdiction are uncertain. It leads to a game where you have a network user or the follower is a wait-and-see decision maker. And the interdictor's objective is now to maximize the expected minimum travel cost for the given interdiction budget. But again, it is under the assumption that the probability distribution associated with uncertain data parameter is known, and that leads to this risk-neutral decision maker framework. So we can again formulate this problem very nicely using random variable C, which has two components, CA and DA, and where C omega A is 1 if interdiction on arc A is successful in scenario omega, and D omega A is the penalty cost of interdicting arc A. And this random variable is defined over a sample space, big omega, which has finite number of scenarios, omega 1, omega 2, so on to omega k. And each scenario, omega, in the sample space has the probability of p omega. So in this case, like the typical two-stage stochastic formulation, the interdiction decisions, which will remain same for the entire network, but the defender, who is a wait-and-see decision maker, will make a decision for each scenario or each realization of the attack and depending on its impact and the success. So pretty much what you will be having is the formulation here is then the interdictor would like to maximize this expected minimum travel cost, which becomes submission when you have finite number of the scenarios. And the defender or follower is now solving again minimum or the shortest path problem, but for each of the scenario where this C omega A, if it is 1, then the attack is successful. So, but if it is 0, then even if arc A has been attacked, it won't impact the cost of the traveling cost to that arc A. And the overall problem is now this, again, a max-min problem, but you're maximizing this expectation. Okay, like I mentioned before, this assumes that the probability distribution is known. That's why we have this P omega, which is known here. But if you don't have the complete information about the probability distribution, and your probability distribution belongs to a set of distributions referred to as an ambiguity set, then the typical idea was, okay, let's use two-stage stochastic distributionally robust formulation, where you will be looking for the worst case distribution. So the interdictor's objective then will be to maximize the expected minimum travel cost, but for the worst case probability distribution. In order to get the worst case probability distribution, since as an interdictor, the objective is a maximization, so you will be looking for minimizing over the set of all distributions. And it arises in application where the interdictor is the main protagonist, or the interdict, they would like to do the interdicting as an evader. Now, one of the things that we notice here is network interdiction problem is also being used to do the vulnerability analysis of a given network, where given a network, you're trying to see what are the most vulnerable arcs in your network that your adversary would like to destroy so that it can have a maximum impact on your objective function. In that case, assuming that my adversary is going to be risk-averse or distributionally risk-averse is kind of me as a defender, or any defender is being a little bit more optimistic here. So maybe I also want to consider, or a defender would also like to consider the cases where my attacker, who by its very nature is willing to accept the risk. So we define that framework as a distributionally risk-receptive network interdiction problem. And from the modeling perspective, there's not a major change that is happening. Essentially, what we are saying is that the interdictor's objective is now to maximize this expected minimum travel cost, but for the best case probability distribution. And here, instead of minimizing from the distributional risk averse case, you are maximizing over the set of distributions, which here one would say, okay, what's the big deal? So from the formulation point of view, it's very neat. But if from the solving point of view, the challenges arise because in this case, oftentimes you have this Q omega X is a concave function. If you take the expectation, you still get a concave function. If you take the minimum of concave function, you still get the concave function. And then it's easy to maximize over a concave function. But if you have Q omega X is still a concave function, maximizing over a concave function will no longer be a concave function. So that's where the challenges arise when you are solving distributional risk-receptive model here. Okay, so just for the illustration, what is happening here is, so you have, again, the same problem. If you will solve the deterministic version of the problem, you will get, this is the optimal solution. Let's say we have two scenarios, omega 1 and omega 2. Omega 1, the interdiction on arc S1 and S2 are successful. and omega 2 is interdiction on arc 1t and 2t are successful. And we assume that the set of distribution has three distributions, P1, P2, and P3, and these are as follows. If I'm going to solve the problem as a risk-averse attacker, so what a risk-averse attacker will do, risk-averse attacker will decide to attack arc S2 and 2T. Why? Because in scenario omega 1, the interdiction on arc S2 is successful. And as a result, the network user will deviate from the original shortest path of which cost 4 units. Now it will cost 8 units because they will go from S to 1 to T. In scenario 2, again 2T will be successful. So the network user will again deviate from the shortest path and will go from S to 1 to T, and it will again cost 8 units. But if I'm going to consider the risk-receptive interdiction solution, risk-receptive interdiction solution is suggesting to attack arc S2 and arc S1, which means that when I consider the scenario omega 1, both arc S2 and S1 has been attacked. And as a result, network users' best path will be S2 1 to T, which will cost them 11 units. And in scenario 2, all attempts will be failed, and thus the network user travel cost will be 4 units. But the expected cost in this case will be very different. So if I consider all three distribution and solve the problem, the risk-receptive solution will cost 8.9 units, whereas risk-averse solution will cost 8 units. So if I'm just assuming my attacker is going to be risk-averse, I'm just considering this lower bound, which is 8 units. I'm not getting really the actual information that I would like to learn about the vulnerability of my network. So this is the paper we had in networks where we have an algorithm to solve the problem. And essentially what this graph is showing, these lines in green are the risk neutral solution where you assume that the probability distribution is known. The orange one are the risk receptive solution, and the blue one are the risk averse solution. So if I only have the distribution risk averse solution, I only have a lower bound. As a decision maker, as a defender, I also would like to know what will be my upper bound if my attacker is willing to take the risk, and your risk receptive solution is telling you that this is the maximum that it can cost you, even if your attacker is going to be accept the risk. So this was a shortest path interdiction problem. We also extended this work to say, okay, let's consider the max flow interdiction problem, where now defenders or the attacker's goal is to minimize the defender's objective of maximizing the flow from source to the sink by removing a subset of arcs given the interdiction budget. And this has been used in nuclear material smuggling or interdicting illicit drug supply, or you want to reduce the supply convoy. So in this graph, if you see the number outside the parenthesis is just the capacity of each arc, and the number or inside the parenthesis is the interdiction cost or the cost to interdict the arc. So very easily you can find in the absence of an interdictor that this will be the maximum flow, which will be flow of 7 units. But if you decide to interdict this arc, then the flow will drop down, and this is the game that is being played. And very easily, this problem can again be formulated for the deterministic version of the problem. You have XA, which are the interdiction decisions, and YA is the amount of flow on arc A. But this will be now a min-max problem, and where when XA is 1, then the capacity of arc A will become 0. But we said, okay, let's look at what will happen if this is done on a multi-stage, which is that the interdiction decisions are being made over a planning horizon. And the interdictor, so in the earlier problem, interdictor was allocating all their budgets in time T0. Now, interdictor would like to allocate the budget over this planning horizon and not to, they might decide to allocate everything in time T0, but we give them the option that the interdictor can remove these arcs over the planning horizon. And we still assume the uncertainty in the capacity, success of interdiction, and the impact of the interdictions. So if you would like to formulate this problem in the deterministic setting, you can formulate this as a multi-stage maximum flow interdiction problem that has already been studied in the literature, where in each time period T, you have this function qt, which is dependent on xt minus 1, which is the interdiction decision that were made in the previous iteration or in the previous time period. And in time period t, you would like to make new decisions xt, which either you decide to attack a new arc, or you decide not, or the arc that has already been attacked, they will continue to remain in that attacked position. And in time period t, the defender will play or will make their move on this interdicted network, which is their max flow problem that they will solve. And here you have your xta are your binary variables, and you have your stage, which are your yta, which are your stage variables. So this framework has been used in the context of disrupting domestic sex trafficking networks and these other city level drug and enforcement framework. Our thought was, okay, let's see what will happen if we want to extend this work by considering there's some uncertainty in the success of the attacks and in the capacity of the arcs in each time period. Very obvious way will be, okay, this is the typical multi-stage stochastic maximum flow interdiction problem, where I have this uncertainty in each time period on the capacity. I can also incorporate the uncertainty on the success of the attacks by bringing some C variable here, a C random variable here. And now instead of just assuming Q t plus 1, I will be considering this expectation over the thing or the scenarios that will happen in the next stages. And here the assumption is that the probability distribution is known. What if the distribution is not known and it belongs to a set of distribution? Then I can have the two additional framework, what is distributional risk-averse framework, where I would like to consider the worst case distribution that I will be able to obtain by taking this max, and the best case distribution that I'll be able to take by considering this minimization. Now, if you notice this inner problem, here you have this min max stuff, but this max is a linear program. So I can very easily take the dual of this problem and make it just a multi-stage stochastic integer program that has been well studied in our community, and you can use that problem to, can use those techniques to solve this particular problem. And as a result, which means that I can consider some extensions of the multi-stage stochastic integer programs where the probability distributions are not known, which leads to distributionally, actually I have a slide here. So this will lead to my multi-stage stochastic program where I have this typical first stage problem with the recourse function, where you have this recourse function corresponding to each stage, and in time or in stage t, from t to 1 to t, you can define your multi-stage stochastic problem using this Bellman equation. And here again, your state variables are xt, which are going from one state to the other. Your stage variables are yt, which are corresponding to that particular stage. So in this framework, we consider this extension has already been considered in the community, where it has been considered that, okay, what if the probability distribution is not known and I want to consider the worst case probability? So I'm going to add this maximization over set of all distributions in each stages. So which will make it as a pessimistic expected cost to go function denoted by Q RA t plus 1 xt. So RA is for risk averse. So QRA, whenever I say QRA, it's expected cost to go function or a pessimistic expected cost to go function. Or in other case, it can be a distributionally risk-receptive framework where I will be looking for the best case probability distribution from this set of distribution. Now, even if I remove or if I just assume that this set of distribution has only one probability distribution and assume that all the variables are continuous, the way to solve these problems is that, or the easy aspect is, because this function Q will be a convex function, so I can, again, when I'm taking this expectation, so I still have the overall problem to be a convex. So it's easier to tackle in that case. But if I'm considering the max of the convex functions, then also I can handle it because it is still a convex. So, but even if I have all the variables are continuous and this function Q is convex, let's say even in the last stage, I still have a non-convex function because I'm taking the minimum of the convex functions. So we consider the problem where this the set or the feasible set in each stage is defined by a set of linear inequalities having integer variables, which is denoted by DRR for distributionally risk-receptive and DRA for distributionally risk-averse multi-stage stochastic integer programs. Like I mentioned, the challenges are the non-convexity of the feasible region, and also the DRR problems are non-convex, even if all the variables are continuous. So these are some of the related literature. So this is more on the stochastic single stage uh, maximum flow interdiction problem, distributionally robust single stage maximum flow interdiction problem, deterministic multi-stage maximum flow interdiction problem. And in the stochastic multi-stage framework, stochastic dual dynamic programming, stochastic dual dynamic integer programming, this is not an exhaustive list, but a lot of work has been done in this literature. In the domain of distributional risk-receptive programs, there are two frameworks the way this problem has been addressed. One is what I just mentioned about analyzing the outcome based on the multiple decision makers' different perspective and varying risk appetite of the decision maker. Other framework that Blanchett and others and Jiang and Shea have considered is in the context of robust statistics, which is just to define, a robust statistics is a statistic that is not highly sensitive to small amount of contamination in the data. It remains stable even when there is a slight disturbance in the data points. So they use the DRR framework for making decisions robust to outliers, errors, and adversarial corruption in data-driven setting. Okay, I won't, as you can see, we don't have much time. And anyway, I plan not to go into the details of the algorithm, but the whole idea is to introduce this distributionally ambiguous stochastic dual dynamic programming, DASDDDP, where the key idea is to approximate this optimistic and QRR and the pessimistic cost to go function by obtaining lower bound convex approximation and then tighten this approximation iteratively. Some assumption that we make that these random variables are stage-wise independent and the support is finite in each stage. And the decision variable or your state variables are binary. So this is your typical stochastic dual dynamic program where the key idea is you obtain the cost to go function is approximated using some optimality cuts. And in 2 seconds, I will say that the key steps are you will sample a scenario path, which is a path from the root node till the leaf node, and you will move in the forward part and will solve the approximation problem until you reach to the leaf node. Then you do the backward step where you will start solving all the child node problems and keep on moving back to the root node to get the better optimality cuts, which will lead to better approximations of the functions that you have. So in a nutshell, the key aspect here is how to obtain a better approximation of these 5 functions, this is the lower bound approximation of your original QRR or QRA function. So we considered 2 different ways of addressing it. One is using the cutting plane based method, other is using the reformulation based method for solving these 2 problems. And we showcase that these algorithms converge to infinite iteration with probability 1. So the key aspect is, I won't get into the details here, is we obtain this lower bounding approximation function for this QRR and use it within your DA-SDDP approach to solve the problem to optimality. Other way of solving it is, since it is an overall minimization problem, I just assume that the probabilities are variables and just that leads to this bilinear terms, and I will use the McCormick relaxation to get a lower bound approximation of this function QRR. I'm quickly scanning through these approaches. The details are in the papers. For solving the DRA, again, we will be obtaining this lower bound approximation using the cuts that we have obtained in the previous iteration and obtaining this probability distribution by solving something called as a distribution separation problem. And for, again, DRA, we also consider this reformulation technique where we use these results known in the literature for the Wasserstein L1 metric-based ambiguity set, where you can reformulate this inner maximization problem into this minimization problem, where then you obtain the lower bound approximation of your QRR function and then try to solve the problem to optimality. So we tested our algorithms for maximum flow interdiction problems and used the instances that were considered in the literature, where you have n is the number of nodes, and this is the number of arcs, and this is the number of stages, and these are the number of scenarios. As you can see, as that's the challenge with the multi-stage problem, the overall number of the scenarios will increase rapidly as you increase the number of stages. And this is just a glimpse, we were able to showcase that the cutting plane based approach is 26.1 times on average faster than the reformulation based approach for the Wasserstein L1 distance based ambiguity set. Pretty much you can see that using this cutting plane based approach, we were able to solve these problems and get the optimal solution for almost all instances. In the reformulation cases, we were not able to obtain optimal solution within this time limit of 3 hours. And the same is for the DRA case. We also considered decision-dependent ambiguity set, which means you have this Wasserstein set, which depends on the decision xt minus 1 and provide this lower bound approximation for your function QRR and showcase that you can solve this problem as well. I'm running out of time. So we also considered the disjunctive constraints, where instead of just considering integer variables or the binary variables, we consider disjunctive constraints. If you consider the problem with two-stage stochastic disjunctive program, this is how your second stage feasible region will look like, where for fixed x and omega, you will have different. So here, this is for fixed x and for a fixed omega. So you see that this is a non-convex feasible region that you obtain. If you're more interested in the details, this is available on, this paper is published, and using this QR code, you can get the paper as well. Just 1 minute, I mentioned, we have extended this in a different frame aspect of, we studied this Stackelberg games with k-submodular function under uncertainty, where we considered the distributional risk receptiveness and robustness. And as a special case, we consider this feature selection interdiction problem, where given a data set and which has a set of features and the data points, and you want to see what are the most vulnerable features in your data set that an adversary would like to destroy so that it can have a maximum impact on your machine learning or a predictive model. So feature selection problem can be formulated as a maximizing a submodular function or submodular maximization problem. We consider the submodular interdiction problem under uncertainty and under the distributional ambiguity, which lead to distributionally robust submodular interdiction problem and distributionally risk-receptive submodular interdiction problem. We have some computational results using Wisconsin breast cancer data that has 569 data points with 30 features and is mainly used for binary classification tasks in machine learning domain. I had all those results, but I won't be able to show. But here you can see that if you use the distributional risk receptive, you can drop down the accuracy of the machine learning model by 82%. In contrast, if you're using distributional risk averse or deterministic or the risk neutral, the accuracy will drop down only till 89%. Okay, just a final conclusion, and this is a little bit, so both optimistic and pessimists contribute to society. The optimists invent the airplane and the pessimists the parachute, said George Bernard Shaw. What we are observing is we need both frameworks, especially when you have these interdiction problems or you want to mitigate the impact of data corruption in your optimization model. Other thing more closer to me and this community are the cutting planes. So cutting planes have played and are playing an important role in the speed up of deterministic mixed integer programs. From here, and this is a slide from Professor Batsima's talk, which showcase how cutting planes or how mixed integer optimization solvers have improved over the time. Cutting planes are based on our observation for these problems. Cutting plane based methods are playing important roles in the speed up of stochastic, distributionally risk receptive, and distributionally robust mixed integer programs as well. with that, thank you, everyone. And this is a joint work. I think Sumin is here. I think I saw him. So if you have hard questions, he will be available. I'm joking. So Sumin and Sungun are the two main lead in both of the work. And I would like to acknowledge the funding by NSF, DoD, and Cyber Commonwealth Initiative at Virginia Tech, or in Virginia, for supporting this research.
Yeah. Thank you very much for the talk. So now, Alex